SwayamPrabha. Digital India. Educated India.
Welcome. So, we have now in lecture 8. So, here we will continue the previous thing, that the calculus of variation. So, this is a small part where we will first we will recap. So, in this lecture we will cover these things, that first variation of a functional involving higher order derivatives, as I have explained in the previous lecture, that we need to know at least second order functionals. So, second order means functionals involving second order derivatives. So, because we will be solving beam problem in this course. So, then we will just do a Euler-Bernoulli beam. So, and then we will also study the first variation of a functional involving several independent variables. So, these are the plan. So, a small recap. So, what we have studied is that we have studied functional, for instance, the functional we have studied. So, functional of this form, that is integral x1 to x2 f of x, y and y prime. So, this we have studied. So, loosely speaking, functional is nothing but a function of function. So, now we have also studied its first variation. So, first variation of the functional we have also studied. So, we have also introduce delta operator. So, first variation of the function. So, this is equals to 0 is the extremization condition. So, this we have studied. Now, in doing so, we have found out the Euler-Lagrange equation of this functional. Euler-Lagrange equation of this functional. So, what is that? So, for instance, the functional involving first order derivative, the Euler-Lagrange equation we have studied is del f or dou f dou y minus d dx of dou f dou y prime equals to 0. So, this is the Euler-Lagrange equation, and its associated boundary condition also we have studied. So, it is a natural consequence of the integration by parts. So, now the boundary conditions are like this. So, at x equals to x1, either dou f by dou y prime is specified, or y at x1 is, so this is specified at x equals to x1, or y at x1 is given. So, now similarly at x equals to x2, either this quantity is specified given, right. So, now this is essentially there are two types of boundary conditions. So, these are boundary conditions. So, these are two types of boundary conditions. So, first one is a natural boundary condition or the force boundary condition, and second one is your Dirichlet or the kinematic boundary condition in case of mechanics. So, now we have also solved one example where a bar problem has been solved. Now, here boundary conditions are mainly two types. So, kinematic or Dirichlet and force or Neumann boundary condition. Now, today we will start if this functional is having higher order derivative. For instance, the functional involving higher order derivatives. So, functionals involving higher order derivative. And its first variation. So, how we can calculate its first variation. So, this is having a direct connection with our beam problem, because beam functionals are involving beam potential energy is involving second order derivative of the displacement. So, which is essentially the curvature. So, now let us choose similar way that functional I is the integral form of the functional f, that is x, y, y prime and y double prime. So, in the similar way that we did for earliest case for the first order case, the same way we will do this. So, first variation I will now go directly instead of step by step. So, this first variation will look like this. So, as we know, that is del dou f by dou y into delta y plus dou f by dou y prime delta y prime plus dou f by dou y double prime delta y double prime. So, now this first two term already we know what we found out the previous case where the first derivative is only given. So, I will directly write those part and then I will accumulate the extra term. So, the dou f by dou y minus your d dx of by first integration by parts. So, first this part is integration. So, first part is dou f by dou y prime into delta y dx. Now, similarly, the boundary condition also will exist, that is dou f by dou y prime delta y at x equals to x1 to x equals to x2. Now, this second term, so the second term again we have to do 2 times by parts. So, I will just do it for the first time. For instance, if I do the first time by parts, then this is nothing but dou f by dou y double prime into delta y prime. This is at x equals to x1 and x equals to x2. then there will be another term minus integral x1 to x2 d dx of dou f dou y double prime into delta y prime dx. So, again we can do this, we can again by parts this quantity. So, I will just write this again x1 to x2 x1 to x2, and then I will keep this term same, dou f by dou y minus d dx of dou f by dou y prime delta y dx. This will remain unchanged, this quantity will also remain unchanged, that is your dou f by dou delta y prime into delta y at x equals to x1 and x equals to x2. Now, the third term, that is also will remain unchanged, that is this will also remain unchanged, that is dou f by dou y double prime into delta y prime. So, now the second term again I will by parts, integration by parts. So, the second term if I do by parts, then there will be a boundary term. So, which will be d dx of dou f by dou y double prime into delta y. So, this will be again x to x1, x to x2, and then there will be plus since minus is there. So, x1 to x2 d2 dx square dou f by dou y double prime into delta y. So, now I will take the delta y term together. So, which will actually give me the Euler-Lagrange equation like in the previous case, that is dou f by dou y minus d dx of dou f by dou y prime plus d2 dx2 dou f by dou y double prime, this into delta y dx. So, this is actually the Euler-Lagrange equation like in the previous case. Now, also I will take the boundary terms together. So, these are boundary terms which we can take together. So, that is your dou f by dou y prime minus d dx of dou f by dou y double prime into delta y. So, this total is specified at x equals to x1 and x equals to x2, and then this third term. So, the third term again is this, third term is again remain unchanged. So, dou f by dou double prime into delta y prime and x equals to x1, x equals to x2. So, now again delta y is a arbitrary variation. So, delta y does not need any considering the arbitrariness of delta y, the variation, we can say that this quantity must be 0, because this is 0 is a trivial solution. So, this must be 0. So, now so the Euler-Lagrange equation is this, for second involving second order derivative. So, dou f by dou y into d dx of dou f by dou y prime plus d2 dx2 dou f by dou y double prime equals to 0. So, this is the Euler-Lagrange equation. Now, similarly for the previous case, we will have boundary conditions specified. So, now at x equals to x1, so either this condition, so either this has to be specified, or the y has to be specified. So, since the variation is 0, basically the variation should be 0 for the admissibility criteria, from the admissibility criteria. Now, at x equals to x1, either this quantity, that is your dou f by dou y prime minus d dx of dou f by dou y double prime, or y at x1 should be given. Similarly, at x equals to x2, either this quantity is given, del f by del y prime minus d dx of del f del y double prime, or y at x2 should be given. So, this is for this part of the boundary condition. Now, there are another part of the boundary condition. So, which we need to take care here, because it is a second order derivative, the functional. So, this part. So, similarly, at x equals to x1, either your dou f by dou y double prime, or so delta y prime is given. So, delta y prime has to be 0. So, here it requires additional admissibility condition. So, now I will say that d y dx at x equals to x1. So, this is also at x equals to x1 is given. Similarly, at x equals to x2, either dou f by dou y double prime at x equals to x2, or dou dy dx at x equals to x2 is given. Now, so this is the whole picture. Now, here we will see with an example how it can be useful for our case, in case of a beam. So, now let us consider a simple beam structure. For instance, if I consider a beam structure of this form, say, so let us see some example. Suppose this there is a beam. So, here this beam could be a simply supported beam. Let us take simply supported beam. So, here suppose there is a UDL. So, W or let us take different. So, Q. So, Q 0 is the load. Now, here we all know what are the boundary conditions. So simply I will come up with the boundary condition from the energy functional. So what is the potential energy associated with this beam? So let us see what is the potential energy. So we all know that is integral 0 to L m square 2 dx is the strain energy, right. So now this is potential energy will be strain energy plus negative of work done. So naturally there will be q0 dx. So sorry, q0 into W is the yes, W is the displacement q0 dx. Now m we all know, that is what is the formula for m. So that is your EI d2W dx2. So this is curvature essentially. Now so we can write the potential energy, that is integral 0 to L. So if I just substitute that, then EI by 2 d2W dx square dx. Now integral 0 to L q0 W dx. So this is my potential energy functional. Now to use the previous result, that is what is our Euler-Lagrange equation. So if you carefully see now that our functional f is this is given, right. So I can just take it those quantities inside and then integrate. So for instance I can take this thing, so integral 0 to L. So this is for our convenience, d2W dx square whole square minus q0W dx. So this is my f. So now I will just use this thing to, so this is my f, right. So if you look carefully, that our f is essentially function of x, because EI Young's modulus and I is your moment of inertia. So all those things can be function of x. So I am just writing function of x, and then this is a second derivative. So this is a function of W also. So W and W double prime. So it's a function of W double prime also. So now interestingly it is not the function of first prime. So that is the slope. So we all know slope is the dw dx. Now if I just find out my Euler-Lagrange equation from this, so what will be my Euler-Lagrange equation? So first let us see what is the form of the Euler-Lagrange equation. So Euler-Lagrange equation, which is dou f by dou w here, right, because w is the variable. Now minus d dx of dou f dou w prime plus d d2 by dx2 dou f by dou w double prime. So this is my Euler-Lagrange equation. So let us now substitute this quantity here. So what is that? So if I just substitute these quantities, I will get the Euler-Lagrange equation for the beam. So dou f by dou w is nothing but minus q0, right. So this is f. So dou f by dou w is minus q0. So this is minus q0. Then minus d dx of dou f dou w prime, that is this quantity is 0 because this is not a function of w prime. So, now this quantity we have to see. So, here if I look carefully, then what I will get? So, that is the second derivative of this. So, now if I take the these things, that is d2 dx2, now here dou f by dou w prime. So, that is ei into d2 w dx2. So, that is equals to 0. So, this is my Euler-Lagrange equation. Now, this Euler-Lagrange equation you are familiar with. So, if I just little bit modify this, then we can say that is d2. So, here this is plus. So, d2 dx square ei d2w dx2 is your q0. So, this is nothing but the beam equation that you have studied for the first year mechanics or later. So, this is the beam equation. So, this is valid from x equals to 0 to L. 0 to L. So, this is nothing but the beam equation. Now, if I take ei constant, then this equation seems to be this, that is ei d to the power 4 w dx to the power 4 equals to q0. So, this is nothing but again the familiar beam equation. We have found out the solution of this equation by the integral means by the integration, double integration method and other things. Now, let us come to the boundary condition. So, in the boundary condition what we have is your the first boundary condition here. So, we will see what is the consequence. So, first let us see the first boundary condition. So, that is dou f by dou w prime minus d dx of dou f by dou w double prime should be given. So, that is equals to given, or your y should be given. So, now so dou f by dou w prime is not there. So, because this is f is not a function of w. So, let us now see what it means. So, d dx of dou f by dou w prime is nothing but your minus dou d dx of dou f by dou sorry, here it is dou f by dou w double prime. So, similarly here it is dou f by dou w double prime. So, that is nothing but your minus d dx of this quantity. So, that is ei d2w by dx2. So, if I take ei constant, then this is nothing but ei d cube w by dx2. So, which dx cube. So, this is again you all know what is this. This is shear force, and so now another so at x equals to, so now let us modify this for this beam. So, at this is x equals to 0, this is x equals to L. Now, at x equals to 0, at x equals to 0, what should be the boundary condition? Because either this has to be specified, or or W has to be specified. So, in our case here W is specified instead of this quantity. So, this quantity is not specified because this is, we know what is the boundary condition. So, at this point the shear force condition is not specified, rather the displacement condition is specified. So, kinematic condition is specified. So, here W is 0. So, at x equals to 0 W is 0, right, and similarly at x equals to L W should be 0. So, here also it is 0. So, this condition is not required here. Now, similarly, another condition, that is dou f by dou y prime and dou f by dou y prime at x equals to x1 and x2 and dy dx, that is the slope boundary condition. So, here dou f by dou prime, so this is the one set of boundary condition. So, we obtained, and another set is dou f by dou w double prime or w prime, that is your dw dx has to be specified. So, if I choose this, so dou f by dou prime, dou w prime is nothing, double prime is nothing but your ei from this functional dw d2w by dx2. So, this is nothing but the moment, we all know. So, naturally for the current beam problem, we have at this equals to 0 our moment, that is m is specified, m equals to 0 here. Similarly, here m equals to 0, the moment specified here, because this is a pin jointed end. So, we can say that at x equals to 0, ei d2w dx2 has to be 0, and at x equals to L, ei d2w dx2 is 0. So, this is the second set of boundary condition. So, you see, for solving the beam problem, there are 4 boundary conditions is required, because the differential equation in terms of displacement in case of a beam is 4th order differential equation. So, that is why we need 4 boundary conditions, and it is interesting to note that these boundary conditions evolved in the first variation of the potential energy function. So, that we have understood from this. So, now I will, the last part of this lecture, I will just briefly mention this. So, we have seen the first variation of the functional in case of a first, means we have seen this kind of functional. So, I of this integral x1 to x2, that is f of xy y prime dx, and also I of this form just now we have studied. So, x1 to x2. So, this is of f of x y y prime and y double prime. So, we know what is the Euler-Lagrange equation for these two functional. Now, if there are more variables, for instance, if I is of this form, that is x1 to x2, if I write now f of x y1 y1 prime y2 y2 prime and so on. So, if I just consider 2 variable, so y1 are y1 and y2 if I consider, then what will be the its Euler-Lagrange equation. So, it is very simple, because we know for this is I am considering the first derivative, functional involving first derivative. So, its first variation will be simply the same thing. So, with respect to y1 we will do, so that is your, this has to be 0, and similarly delta 1 I with respect to y2 has to be 0. The same procedure if I follow, then I will arrive to Euler-Lagrange equation for two different variables y1 and y2. Those are, say, dou f by dou y1 minus d dx of dou f dou y1 prime equals to 0 and dou f by dou y2 minus d dx of dou f dou y2 prime has to be 0. So, similar to this, the boundary conditions. So, this is Euler-Lagrange equation. So, this is Euler-Lagrange equation and boundary conditions are similarly specified. So, the boundary condition has to be in the both the variables. So, either dou f by dou y1 is specified, y1 prime is specified, or y1 is specified at x equals to x1 and x2 and x2. So, similarly either either dou f by dou y2 prime or y2 at x equals to x1 and x2 is specified. So, this is just an extension. So, similarly for the second order for the second order functional involving second order derivative, we can found out. For instance, if the functional look like this, that is your integral x1 to x2 f of x y y1 y1 prime y2 y1 double prime and then y2 prime and y2 double prime. So, this is just an extension of what we have done. So, this I think one can easily derive from this thing. So, this is the end of lecture 8. So, in this thing what we have studied mainly three things. So, first we have studied the how to find out the Euler-Lagrange equation of functional involving higher order derivatives. We have also found out one example which is very common for structural engineers or mechanical engineers, is a beam. So, beam problem we have seen that how it is related to, and then we derived the governing equation of the beam and its associated boundary condition, which is a directly from the Euler-Lagrange equation and its boundary condition form. And then we have also briefly discussed that if the functional is involving multiple variables, for instance y1 and y2, this is also is going to how to derive the Euler-Lagrange equation for this. So, so I stop here. So, we will meet in the next lecture. So, thank you.